So this is going to be Recitation 9C. It's going to be the last of the Chapter 18 material, but this is where many of the detailed and more challenging topics and aspects lie. So the first thing to know is for aldehydes and ketones in general, they only undergo two types of reaction. Those types of reaction are nucleophilic addition and condensation. We'll get to condensation in a moment, but primarily we're going to talk about nucleophilic addition. So addition means two atoms or groups getting connected at the expense of your pi bond, and the polarity of the CO double bond, carbon partially positive, oxygen partially negative, means that a nucleophile always gets connected to the carbon, and the other group that's added must be to the oxygen, and in all your cases that other group will be a proton. So nucleophilic addition is just addition of a nucleophile to the carbon, addition of a proton to the oxygen, adding two new atoms or groups across your carbon-oxygen pi bond. So there are many different nucleophiles that can be employed in this nucleophilic addition reaction. Long list of them. Some of those are in your notes, but it applies to any nucleophile. Any nucleophile is the same, it's just a 2-electron donor. It could be a simple nucleophile like OH-, could be a more complicated one like lithium aluminum hydride or sodium borohydride. Doesn't matter, every nucleophile, 2-electron donor, does the same thing for aldehydes and ketones, always gets connected to the carbon. So for the mechanism of nucleophilic addition, there are two different mechanisms. Obviously, we have to make two new bond connections. Excuse me. The nucleophile's got to connect to the carbon, the proton has to connect to the oxygen. And the timing of those two steps can vary depending on what reagents and conditions you have present in your reaction. So it's basically a race. The nucleophile is going to connect to the carbon, the proton is going to connect to the oxygen. The question is which happens first. So it depends on how strong or good your nucleophile is, and it depends how good whatever species you have present at protonating things. So nucleophile strength and acid strength for your given system will determine the order or the sequence of those two required steps. So if you have a very strong nucleophile and you have either a weak acid or something that's not acid at all, your nucleophile is going to connect fastest, meaning first, and then the protonation will occur second. That's what we call basic conditions, right? You can see it there in bold black in the nucleophilic addition box next to that transformation. Nuc, then proton, means nucleophile first, protonation second. However, you can also do these nucleophilic additions under very acidic conditions. This allows you to get protonation first, then nucleophilic attack second. So nucleophilic additions work for aldehydes and ketones, and they work under acidic conditions, and they work under basic conditions. You might look back at some of the previous reactions and see that they're nucleophilic additions, right? Aldehyde to secondary alcohol, nucleophilic addition. Aldehyde to primary alcohol, nucleophilic addition. So wide set of different transformations for aldehydes and ketones, but that one general reaction type of nucleophilic addition. The next and really the only other type of reaction that aldehydes and ketones both do is a condensation reaction. Now, a condensation reaction is a new class of reaction. So far, we've previously done addition, elimination, and substitution. Definition of a condensation reaction is when two or more molecules connect together, join together, but that's also accompanied by the expulsion of a small molecule. Most of the time, that small molecule will be water. Doesn't have to be, but most of the time it will be. And for you, there are three important condensation reactions that you must know. Or I guess, if we're doing open book, that you must recognize. So we're now looking at the condensation row in our bottom third of the summary. So the blue one involves now the formation of a functional group with a carbon-nitrogen double bond. So in general, those are called imines. We'll talk in chapter 19 about all the different functional groups that have nitrogen. So aldehyde or ketone to imine is done with some, and it can be a variety of different substituents. Here we just got it listed as Z, NH2, and acid conditions. We can also form what's called an acetal. So this is now the red molecule. So a carbon connected to two OR groups. And then we also have the pink version next to it, which is called a cyclic acetal. So it's like an acetal, but the two oxygens are connected to one another through some type of carbon linkage. So it's an acetal, but it's cyclic, creatively called cyclic acetal. So for you, these are the three versions of condensation reactions that you need to know. So the mechanism for a condensation reaction is a nucleophilic addition followed by some other step. For the imine formation, it's a nucleophilic addition followed by an elimination. For the acetal and cyclic acetal, it's nucleophilic addition followed by nucleophilic substitution. The mechanisms for those three processes are all in the notes. Aldehydes and ketones both undergo nucleophilic additions and both undergo condensations. Even though there's a wide variety of reactions, aldehydes and ketones undergo nucleophilic additions and condensations, and essentially that's it. So lots of chemistry, but the oversight is just two general types. The next issue, which is on the top right of that bottom third of the summary, is the statement that aldehydes are more reactive than ketones. So aldehydes and ketones both do nucleophilic additions, both do condensations. However, aldehydes will do those same reactions quicker than ketones. So aldehydes more reactive than ketones. Two reasons as stated in your notes: because of sterics, because of electronics. So you have to be careful that these designated sets of reagents will react with aldehydes and with ketones. So it's going to be easier to illustrate this next section, which if you use the diagram on chapter 18, page 37. And in the middle of that page, so that was chapter 18, slide 37. In the middle of that page, you have a start material that has the green aldehyde and the red ketone. So here's a molecule that has both an aldehyde and a ketone. Aldehydes and ketones react with the same reagents, but aldehydes will react more quickly than ketones. So if you want to do chemistry on the aldehyde and not react the ketone, it's straightforward. Just add one equivalent of your reagent and the reaction proceeds. If you add two equivalents of the reagent, it will do the aldehyde first, and then it will do the ketone. The more challenging transformation is to get your ketone to react, but not have your aldehyde react. Chemists want to be able to do every transformation in every possible way with every degree of control. And this then raises the topic that we call a protecting group. So a protecting group allows you to, as its name suggests, protect a functional group from reacting when it normally would. And so on slide 37, we have an overall transformation where we're reducing a ketone to a secondary alcohol. So that's lithium aluminum hydride followed by H3O+. But our aldehyde is remaining unchanged. Initially, that may seem like an easy transformation because you'd say, well, ketone to secondary alcohol, hydride reduction. But the complication here is that that reagent would preferentially react with your aldehyde. Why? Because aldehyde's more reactive than ketones. So what we have to do is protect our aldehyde to stop it from reacting. We need to employ this strategy that we're calling protecting groups. The protecting group that we're going to use is a cyclic acetal. Cyclic acetals do not react with nucleophiles because it's formed in a condensation reaction. All of the condensation reactions require acid. That's the connection. So on slide 37, we add the reagent set of diol and acid to form a cyclic acetal. Could form a cyclic acetal on the aldehyde, could form a cyclic acetal on the ketone, but aldehyde's more reactive than ketones. So the cyclic acetal is formed on the aldehyde. Now, when we have a cyclic acetal and a ketone, only the ketone will react with the strong nucleophile in the reagent lithium aluminum hydride. So it's the ketone that gets reduced. Then we add acid to protonate the O-, and we need also to convert our cyclic acetal back to an aldehyde. We do that with H3O+. So you will see in the top right-hand corner, we're now back on the summary page where it says aldehydes more reactive than ketones. And then in pink, cyclic acetals as protecting groups. So our strategy is, if you don't want your group to react, you convert your aldehyde to a cyclic acetal. Reagent set is next to it. Do whatever chemistry you then want to do wherever else in your molecule. And then, when all the chemistry is done, you remove your protecting group, which is what we call deprotect. So in blue, you can see there, deprotect with H3O+. And that then converts your cyclic acetal back to the original aldehyde. So our strategy overall is protect the group we don't want to react, do our chemistry, and then when we're done, deprotect to liberate the unchanged functional group. So that's then a strategy of being able to control exactly where our reaction takes place based on the understanding that aldehydes and ketones react with the same reagents, but aldehydes are more reactive than ketones. At the bottom of that summary page, we then have the Wittig reaction, which is really just a nucleophilic addition that then goes awry. The reason why it's a famous reaction is it makes alkenes. Obviously, carbon-carbon double bonds, very important. And then at the bottom of that page, we have the reduction section. So if we talk about functional group interconversions, aldehyde or ketone to corresponding alcohol, reagent set C, that's a reduction, hydride reduction followed by protonation. We also learned in our alcohols chapter that alcohols can be converted into tosolates and then reduced. That's just a substitution. That would be reagent set D. What we're talking about now is the overall transformation from aldehyde or ketone to alkane. That two-step reduction process, that overall process is given a new name. It's called deoxygenation. As its name suggests, de means remove, oxygen means, guess what? Oxygen. So deoxygenation means you are formally removing oxygen. Notice that your aldehyde or ketone has 1 oxygen, alkane has 0 oxygens. So using existing chemistry, so transformation C, transformation D, you can achieve deoxygenation. But you can also do that two-step process in one step. So you've already seen one way to do that. Reagent set A, the zinc mercury HCl, you would recognize from our previous chapter as the Clemmensen reduction, primarily used when we had our aromatic ketone produced by Friedel-Crafts acylation. Clemmensen reduction would convert the acyl group into the alkane. That would be a way of getting Friedel-Crafts alkylated products that we couldn't get directly. There is another way to do that deoxygenation in one step, and that's using NH2, NH2, and KOH, known as the Wolff-Kishner reduction or Wolff-Kishner deoxygenation. You might say, well, why do I need 2 ways to do deoxygenation? The difference here is one is acidic and one is basic. There might be times when you don't want to use acidic conditions because somewhere else in your molecule is sensitive to those conditions. I don't know, like if you have an acetal present. So acid and base versions of doing deoxygenation, that works for aldehydes and ketones. So aldehydes and ketones, lots of reactions, but when we take an overview of how are these reactions different, aldehydes and ketones both do nucleophilic addition, both do condensation, but aldehydes do them more quickly than ketones. That gives us a relative reactivity issue that we can handle if necessary using our protecting groups. The protecting group of choice is the cyclic acetal.